All right, we're thinking about magnetic induction now, or electromagnetic induction, I really should say. Ordinarily, when you want to get a current, you, you give your circuit a potential difference by connecting it to a battery or plugging into a wall socket. But there are other ways to produce potential differences a little bit more indirectly. We call that induction. And one way to make that happen is really, in a sense, you can think of it as a result of magnetic force. Let's imagine this wire loop made of conducting material, and it's falling. And here's a region of magnetic field, and the loop is partly inside, partly outside that region of field. So that is these parts of the loop that are in the magnetic field region have electrons, things that can be used for to create current. So these electrons are actually moving through a magnetic field. And what happens when a charged particle moves through a magnetic field? It feels a force. So think about the electrons here in this top part of the wire. They're all moving this way, and they're feeling a magnetic force this way. So they're feeling a magnetic field this way. So what's the direction of the force that those electrons would feel? Well, let's use the right-hand rule. Remember how that goes. First, thumb in direction of the moving charges, right? They're all in this loop which is falling, so the direction of velocity for all those charged particles is this way. That's the direction of the thumb. Point your finger in direction of the electric field, which is out, coming straight at you, perpendicular to the blackboard, away from the blackboard, and then make your other three fingers, rotate them so that they're perpendicular to index finger and thumb, and then when you do that, they'll be pointing in the direction of the force on a positively charged particle, which would be a force this way, but the electrons are actually feeling a force in the opposite direction because they're negatively charged. So the electron force on the electrons is this way. That is, electrons will be pushed this way. They'll start to move this way. And when we think of, instead of electron flow, we think of the so-called conventional current, in which we imagine the moving charges that make up the current are positively charged particles. So negative charge moving this way is the same as positive charge moving the other way. So you've got some charge moving that way. And what about the electrons in these vertical parts of the loop? Well, they're all moving in the same direction as these electrons. They're feeling a magnetic force in the same direction as these electrons, so they'll feel a force in the same direction. Right? The electrons here will feel an electric force pushing them this way, but they can't really go anywhere because there's not much space there between the two sides of the wire. And likewise here. So the only place where you can actually get a force and get electrons to move is this way, or movement is this way. So electron flow would be clockwise, and the conventional current would be flowing counterclockwise. notice one important thing. That's only going to happen as long as you've got one side here in and another side out of the magnetic field. Because if the electrons here in this part were inside the magnetic field, they'd be moving this way and feeling a magnetic force this way. Thumb in direction of velocity, index finger in direction of the magnetic field. Rotate the fingers, and that gives you the direction of the force on a positive charge this way. So electrons would feel a force this way. Electrons down here would feel a force to the right if this were in a region of magnetic field. And so there would be conventional current, positive charge, pushed to the left if this were in the region of magnetic field. And what would we have? We'd have some charge going this way, and then because charge down here is pushed right to left, we'd also have an equal amount of charge going the other way. They just cancel each other out, and you get zero net current. You have equal amount of current being pushed this way and then being pushed clockwise, and they just cancel each other out. In other words, you get that current pushed around only when this loop is part in and part out of the magnetic field. That'll be an important point later in tomorrow's topics. But here's a current. We know that you don't get current unless there's a potential difference. So somehow a potential difference was generated inside this loop without having to attach it to a battery or a wall socket. And that's what we mean by electromagnetic induction. You indirectly induce a potential difference and a current without connecting to a battery. So look at one other example like that. Let's say you've got a big horseshoe magnet, and then here's the south pole, and then here's the north pole of the horseshoe magnet. You've seen in the reading that magnetic field lines always point away from a magnet's north pole and always point toward a magnet's south pole. So in the region between these poles, the magnetic field is pretty much just straight vertical field lines going from north to south. That's the magnetic field. And now imagine that we have a current loop, a loop in a horizontal plane, a loop in a plane that's perpendicular to the plane of the blackboard. So here's just sort of the edge of that loop. And imagine we're pulling that loop to the right. So the loop has some velocity to the right. And that's going to turn out to look a lot like this, because in both cases we have a loop that's partly in and partly out of a region of magnetic field, right? Just this part of the loop is inside magnetic field. And so the charged particles in this part of the loop will then feel a magnetic force, and that'll start pushing them around and again create current. Let's see what the current is like in this case. So thumb in direction of the velocity, index finger in direction of the field, and then rotate your other fingers so they're perpendicular to thumb and index finger, and that points this way, which will be the direction of the force on positive charge. And so let's just think about the conventional current. We imagine positive charge moving. So positive charge here on the left side of the loop is being pushed this way. So in other words, when you see the current right here at the left edge, right at the very left edge of that loop, it's coming at you because it's being pushed this way by the magnetic force. So there's our symbol for something that's pointing at you, perpendicular to the paper, and then the current will move this way. And so here on the right side of the loop, the current will be moving away from you, pushed towards you on the left side of the loop, and then away from you on the right side of the loop. And then that, again, just like in this case, that current exists only while this loop is part out and part in. Obviously, if it's completely out, there's no magnetic field, so there can be no magnetic force to push charged particles around. And if it were entirely inside the loop, then you'd have the same situation like this. You'd have one side of the loop in which current was pushed one direction, and then the other creating a counterclockwise current, and then another side of the loop being pushed by force of the same direction, but since it's on the other side of the loop, that creates a current that flows in the opposite sense, clockwise, and then a clockwise and counterclockwise current just cancel each other out for no net current. Okay, that's the idea. And notice what was actually changing in this part and in this part. What was actually changing was the amount of loop area actually inside the field region. It was that specifically that gave us our induced voltage and induced current. And so the thing that we're really interested in here is something called magnetic flux. And it will be changes in that so-called magnetic flux that actually produce the induced voltages and the induced current. Magnetic flux, our definition is like this. So again, here's just imagine another loop. We're seeing the edge of the loop. The loop is in a plane perpendicular to the blackboard, and then here's the axis of the loop, right? The line going through the center of the loop and perpendicular to the plane of the loop. And then there's some kind of magnetic field, could point in any direction. Let's say it's pointing this way. So then we take note of the direction of the angle with respect to the orientation of the loop by looking at, or the direction of the field with respect to the orientation of the loop by looking at this angle here, angle between the field and the axis of the loop. Okay, and then we define this thing called magnetic flux, capital Greek letter phi, and it's a product of three things: just the area of the loop, and the strength of the magnetic field, and cosine of that angle between the axis of the loop and the direction of the field. So in other words, if this loop were rotating, then of course this factor here would be changing, and that would change the magnetic flux. As it turns out, as we'll see in the next reading and the next exercises, it's that change in magnetic flux that is really specifically responsible for giving us the induced current and induced voltage. So just look at an example of this. Let's say here's some magnetic field. And then we've got a loop, maybe perpendicular to the direction of the field, and then changes direction so that now it's say a 60-degree angle, or rather, here's the angle between the axis of the loop and the direction of the field, and let's say here it's 30 degrees, and then it rotates some more, so that now it's, let's say, like this. There's the axis of the loop, and now the angle between the axis and the direction of the field is 45 degrees. And then it rotates some more so that now there's the loop, there's the axis, and the angle between the axis and the field direction is 90 degrees. Well, as the loop goes from this orientation to this orientation, the flux decreases. But, here, the angle between the axis of the loop and the direction of the field, they're the same direction, so the angle between those directions is 0. Cosine of 0 is 1. So here, the flux is just as big as it's ever going to be. It's just field strength times area. And here, now, the angle between axis and field direction is 30 degrees. So we have cosine of 30 degrees, which is about 0.87. So the flux here is equal to 87% of B times A. And then here the angle is 45 degrees. Cosine of 40 degrees is about 0.71. So here the flux is about 71% of B times A. And then, of course, here, where the angle between the field direction and the axis is 90 degrees, cosine of 90 degrees is 0, no flux at all. No flux at all for that case. That suggests a simple way of thinking about flux as you let me redraw this picture to illustrate that simpler way. So here's a bunch of field lines. And here's the original orientation of the loop. Let's say it's like that, make it a little bigger loop, and then rotates. And then rotates some more. And then rotates some more. And then rotates some more. And you see what's happening at different orientations, at different angles between the field direction and the axis. different numbers of field lines pass through the loop. Right here, where the loop is perpendicular to the field direction, we get the largest possible number of field lines passing through. And then obviously if the field is perpendicular to the axis of the loop, you have no field lines passing through. Well, this situation, which had, remember, corresponded to the maximum possible value of flux, this corresponds to the minimum value of flux, 0. And as you go from this situation to this situation, as we saw in the more numerical example, as the angle between axis of loop and field gets bigger and bigger, as it goes from 0 to 90, the flux decreases. But also, as the loop rotates from this state to this state, as the angle between the axis of the loop and the field direction goes from 0 degrees to 90 degrees, fewer field lines pass through. Fewer field lines pass through the loop. So pictorially, you can imagine flux as just a way of measuring how many field lines pass through the loop, or flux is some number that's proportional to the number of field lines that pass through the loop. More field lines means stronger flux, fewer field lines means less flux. And that's a helpful way to think about it. Right now we just have a few simple exercises to get used to the ideas of induced currents and induced voltages and magnetic fluxes. And then in tomorrow's reading and tomorrow's assignment and tomorrow's video, we'll see how those two things actually fit together.